The diet of fossil birds, or avialans, everything including living birds as well as their relatives as distant as Archaeopteryx, is almost entirely unknown. There's over 150 species of Mesozoic birds, but out of those we only have 6 that we really have any good idea of what they ate. They actually have a meal preserved inside their stomach as a fossil, and because of that we know at least one of the things that they ate. That's not to say there haven't been plenty of theories about other birds. There's dozens of statements of this thing had large teeth, so it must have been eating hard animals or something like that. But that's all very qualitative. It's not something that can be reproduced in a scientific manner. So, my co-author and I have reviewed the literature of both how we figure out the diet of living birds, as well as fossil theropods, the closest relatives of birds, in order to figure out what techniques we can use in order to figure out the diet of fossil birds. Ultimately, we came to settle on 7 lines of evidence: dental microwear, cervical muscle reconstruction, stable isotope analysis, body mass analysis, pedal traditional morphometrics, lever modeling of the skull, and finite element analysis of the skull. Dental microwear looks at the hardness, or resistance to fracture, of foods, as well as toughness, resistance to tearing, in an animal's diet. So as you can see here, we can look at these extreme close-ups of animal teeth and look for pits and scratches in them. Usually pits will imply that there are more hard things in the diet, whereas scratches imply more tough things. And then we can look at cervical muscles, the muscles of the neck. This can tell us how animals would use their head both to acquire and disassemble food. So for instance, we might expect a fish eater to be lifting its head up quite often in order to lift fish out of the water, whereas a seed eater would need strong muscles to move its head up and down for a plucking motion. And then we have stable isotope analysis, which is relatively straightforward. We know from living animals that as you go up a food chain, nitrogen 15 tends to increase in the animal tissues, while calcium 40 tends to decrease. And so when we compare animals all from the same area, we can get an idea of what their relative positions in the food chain were based on the nitrogen and calcium isotopes in their body. Then we look at body mass. So in some recent studies of birds, it was actually found that body mass explains more of the quantified diet of birds than just about anything else. We don't exactly know why yet. I personally would assume that it's larger birds are eating larger things. And then on to traditional morphometrics, the way that we quantify the shape of an object based on a combination of linear and angular measurements. This is very effective at detecting raptorial use of the claws in living birds. So birds that are taking their claws and using them to either kill an animal or to hold it in place while they kill it. And so what we're looking for with this is an enlarged first and second digit, basically like the thumb and forefinger in us that is used to grip and hold on to the animal, and a high curvature of the claws used to wrap around things. And then lever modeling. Most animal jaws can be reconstructed as a third-class lever, the simple machine. And using equations that we apply to levers, we can show the efficiency of the jaw, whether it's more adapted for biting fast or biting hard. Typically, carnivores tend to have fast jaws and herbivores tend to have strong jaws, though there may be exceptions to this. For instance, in a lot of bone-crunching mammals, they also have jaws adapted for putting a lot of force out. And then finally, finite element analysis. This is an engineering technique where we take irregular shapes, like say an animal jaw, and split them up into a bunch of squares and triangles, so that we can tell how they react to being loaded like a bite. This gives us an idea of the jaw's strength, whether these animals were capable of eating very hard foods, possibly struggling animals, or if they would have to stick to soft foods they can just bite through very easily. So, taking this new framework into account then, what new have we learned about the evolution of bird diet? Well, unfortunately, the ancestral avialan diet is still really obscure. Archaeopteryx actually has conflicting information from these different lines of evidence. We personally think that has to do with the fact that all of the quantitative analyses have been done on different sets of individuals. And so very likely there is variation within Archaeopteryx itself, that different individuals ate very different things, possibly even different populations adapted for different things. And so ultimately we have to kind of leave that question open for now. We can say, though, that Confuciusornis, both the efficiency and strength of its jaw, look pretty herbivorous when you put them together, whereas Schenkiornis and Enantiornithine, it has a relatively quick jaw like a carnivore, and its claws look raptorial. So without even doing any new work, that's 2 new bird species that we can add to our list of known diets. But in total, that's still only 8 out of over 150 species. So it's obvious there's still a lot more work to do, but now at least we have a nice quantitative roadmap that we can use to figure out the diet of Mesozoic birds.